Okay, now we can see what is the Smith chart and how it is used for impedance matching. But before moving into impedance matching, we should know what is the necessity of impedance matching. So then why it is important. Actually, there are mainly 3 points regarding it. That is, first one is for the maximum power transfer from the source to the load. And second one is to avoid the damage to the source or the transmission line. And third one is to keep the losses, the transmission line low. We don't want to go to much details. And this one here is a basic form of a Smith chart. You can see here in the horizontal axis, it is the reflection coefficient, real part of the reflection coefficient, and on the vertical axis, it is the imaginary part of reflection coefficient. And at the center, the magnitude of the reflection coefficient is 0. And in this final form, you can see these crazy lines over here, and nothing much to worry about it. That Smith chart is a combination of two types of circles. First one is the R circle, and second one is the X circle, and we will move to that. This one here, this is an R circle. You know, that means this value is here 0.512. These are normalized resistance. Normalized, I mean, in simple words, the real part of the load. As the load value is a complex number, this values right here is the real part of it, or it is the normalized resistance. See that one. And this is the X circle. See these values around here, minus 0.5, minus 1, minus 2, 1.50, and these values are the complex side of the load impedance. This can be inductive, capacitive. Okay, now we can move into the impedance match. How impedance matching is done with the help of Smith chart. Before that, I need to say one thing, that to achieve perfect matching, we want the load impedance to match to the transmission line impedance. That is ZL. That is ZL equals Z0. The load impedance should match the input transmission impedance. But this Z0 is a characteristic impedance. But we take that as input impedance. Z is equal to Z0. That's why ZL should be equal to Z0, and that is the impedance matching. So I think the most simple way for this impedance matching is by using a series inductor or a series capacitor. That means in case of series inductor, an inductive element is placed in between the source and the load in the transmission line. Series like this. See, the L is this placed between the source and the load impedance. So what happens when this inductor is placed here? The load impedance has a reactance part, that is ZL equals R plus Ix. So inductor also has a reactance part. and as it is in series, it will the reactance of inductance will add with the x of ZL. I'll explain again. As inductor is a reactive element, it also has a reactance, a positive reactance, and it can be positive or negative. I'm sorry. The reactance will add with the reactance part of the load here. Okay, and the reactance of inductor, you all know that 2 pi fl I 2 pi fl as an imaginary case. So while doing the impedance matching, we should consider the normalized normalized reactance. So how to take the normalized reactance is that just divide it by the characteristics impedance. So the normalized value of the inductance impedance is this. You should always take like this. So as it is in series, it will add with the x component that I said earlier. So x plus 2 pi fl by z0 I, and that's that. Now see the chart. This all here is the reactive part, and this is the real part, which is the resistance of the load. So what we are trying to do is we need to get rid of this term, this reactive part. So just equate it with 0. Okay, consider an example. It's a tau equal to 1 minus 2y. So in the chart, see, this point is our ZL. We can see that this line here minus 2, which is a reactive part in the example, and this circle line here was to 1, which is a real part, is in the example we mentioned. See, 1 minus 2y, the reactive part and the real part. So we should find the appropriate inductance should be added in series to cancel out this term and to get impedance purely real. So we added the term 1 minus 2y. Okay, it is again, sorry, there's a minus 2y here. Okay, and this is equate this part to 0. Okay, sorry, to 0. Let f equal to 10 raised to 9 hertz, and Z0 is 50 ohm as usual in the coaxial cables. So from this we can find the inductor value is equal to 15.9 nanohenry. So when 15.9 nanohenry is installed in series with the inside in the transmission line between source and the load, in the Smith chart here, this point will move towards the center from here to here and follow this path, and it will be at 1. So this is what impedance matching in terms of Smith chart is. We want to move the impedance to the center of the Smith chart where the reflection coefficient is 0. See, center, the reflection coefficient is 0 at the center, like I said earlier. While drawing this chart, one must be at the center, but in this circle it is not at center, but it should be at the center. You can follow the similar steps while using a series capacitor, but the movement of the from the is just opposite of any series inductor from here on top of the Smith chart.